For most of human history, the question of life beyond Earth belonged to philosophy and imagination. Today, it belongs to science. We live on a small rocky planet orbiting an ordinary star, in a galaxy that contains hundreds of billions of stars, and in a universe that contains hundreds of billions of galaxies. On this scale, Earth is not special by position. It is not at the center of anything. It is not located in a unique region of space. It is simply one world among countless others. And yet, as far as we can tell, it is the only world known to host life. So the question remains open. Are we alone in the universe, or is life a common outcome of cosmic evolution? To answer that, we need to understand what we already know, what we do not yet know, and what science is actively searching for. Until the 1990s, we did not know whether planets were common around other stars. The only planetary system we had ever observed was our own. That changed in 1995, when astronomers detected the first confirmed exoplanet orbiting a sun-like star. Since then, the pace of discovery has accelerated rapidly. Today, we have identified more than 6,000 confirmed exoplanets, with thousands more awaiting verification. We now know that planets are not rare, they are the rule. Observations show that most stars host planetary systems. Many stars host multiple planets. Some systems contain tightly packed families of worlds orbiting close to their star. Others resemble our own solar system, with rocky planets close in and gas giants farther out. The diversity is remarkable. There are planets larger than Jupiter but lighter than Saturn. There are worlds made mostly of water. There are super-Earths several times the mass of our planet. There are planets orbiting two stars at once. There are worlds with years lasting only a few hours. Nature appears to be very good at making planets. Among all these worlds, scientists are especially interested in planets that orbit within what is called the habitable zone. The habitable zone is the region around a star where temperatures could allow liquid water to exist on a planet's surface. Not too hot, not too cold. On Earth, liquid water is essential for life. Every known biological process depends on it. This does not mean that every planet in the habitable zone has water. It only means that water could exist there under the right conditions. Some of the most studied systems include TRAPPIST-1, which hosts 7 Earth-sized planets, several of them in or near the habitable zone. Others include Proxima Centauri b, orbiting the closest star to the Sun, and dozens of newly discovered super-Earths around nearby red dwarf stars. These planets are not Earth. Many are larger, denser, and orbit stars very different from our Sun. But they show that potentially habitable environments may be widespread throughout the galaxy. Life on Earth is built from a small set of chemical elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These elements are not rare. They are forged inside stars and distributed through space by supernova explosions. Over billions of years, they accumulate in clouds of gas and dust that eventually form new stars and planets. Astronomers have detected complex organic molecules in interstellar space. Amino acids have been found in meteorites. Water exists on Mars, on icy moons such as Europa and Enceladus, and in vast clouds between the stars. The raw ingredients for life appear to be common throughout the cosmos. This suggests that the chemical pathway toward life may not be unique to Earth. Under the right conditions, similar processes could unfold elsewhere. Despite decades of research, we still do not know exactly how life began on Earth. What we do know is that life appeared relatively early in Earth's history. The planet formed about 4.5 billion years ago. The earliest evidence for life dates back at least 3.8 billion years. That means life emerged within a few hundred million years after Earth cooled enough to support liquid water. This suggests that, under the right conditions, life may arise relatively quickly on a planetary timescale. However, we do not yet understand the precise sequence of events that led from simple chemistry to the first self-replicating organisms. This remains one of the great unsolved problems in science. In 1961, astronomer Frank Drake proposed a simple framework for thinking about the number of technological civilizations in our galaxy. His equation does not give an answer. It organizes our ignorance. The Drake equation multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction of those where life actually appears, the fraction that develop intelligent life, the fraction that develop technology. The length of time such civilizations release detectable signals. We now have good estimates for the first few terms. We know stars are abundant, we know planets are common, we know potentially habitable worlds exist, but the biological terms remain unknown. We do not know how likely life is to emerge. We do not know how often intelligence arises. We do not know how long technological civilizations survive. The result could be that the galaxy is filled with life, or that we are alone. Both remain scientifically plausible. If intelligent civilizations are common, then a troubling question arises. Where is everyone? This is known as the Fermi Paradox, named after physicist Enrico Fermi, who asked why we see no evidence of extraterrestrial technology in a galaxy that is billions of years old. Even with slow spacecraft, a civilization could spread across the galaxy in a few million years, a short time compared to the age of the Milky Way. If such civilizations were common, we might expect to see signs of their presence, yet we see none. No probes, no megastructures, no clear signals. This absence of evidence does not prove that no one is out there, but it does demand explanation. There are many proposed explanations for the Fermi Paradox. One possibility is that life itself is rare. Perhaps the origin of life requires such specific conditions that it only happened once. Another possibility is that simple life is common, but complex life is rare. On Earth, single-celled organisms dominated for billions of years before multicellular life emerged. Another idea is that intelligent life is rare. Intelligence may not be an inevitable outcome of evolution. There is also the possibility that technological civilizations tend to destroy themselves before they spread beyond their home world, or that they choose not to communicate, or that we are simply too early. The universe may be only beginning to produce technological civilizations, or that we are looking in the wrong way. Before looking across the galaxy, scientists are searching much closer to home. Mars was once warmer and wetter than it is today. Ancient riverbeds and lake basins suggest that liquid water once flowed on its surface. If life ever arose on Mars, traces of it may still exist underground. Europa, a moon of Jupiter, hides a global ocean beneath its icy crust. That ocean contains more water than all of Earth's oceans combined. It is kept warm by tidal heating from Jupiter's gravity. Enceladus, a moon of Saturn, has geysers that spray water and organic molecules into space. Spacecraft have flown directly through these plumes and analyzed their composition. Titan, another moon of Saturn, has rivers and lakes of liquid hydrocarbons. Its chemistry resembles a laboratory for prebiotic experiments. If life exists elsewhere in our solar system, it would demonstrate that life can arise more than once in a single planetary system. That would strongly suggest that life is common in the universe. Beyond our solar system, astronomers search for life by studying the atmospheres of distant planets. When a planet passes in front of its star, some starlight passes through its atmosphere. By analyzing this light, scientists can identify the chemical composition of the atmosphere. Certain gases are especially interesting. Oxygen, ozone, methane, and carbon dioxide can be produced by biological activity. On Earth, their coexistence is maintained by life. The James Webb Space Telescope is now capable of studying the atmospheres of small rocky planets around nearby stars. Future missions will go even further. However, detecting life this way is extremely challenging. Many non-biological processes can produce similar chemical signatures. Any claim of life will require extraordinary evidence. Another approach is to search for technological signals. This effort is known as SETI, the search for extraterrestrial intelligence. Radio telescopes scan the sky for narrowband signals that could indicate artificial origin. Optical telescopes search for brief laser pulses. Some scientists also search for unusual infrared signatures that could indicate large-scale energy use. So far, no confirmed extraterrestrial signal has been detected. This does not mean no one is transmitting. It may mean that we are listening on the wrong frequencies, at the wrong times, or in the wrong way. Or it may mean that technological civilizations are rare. One of the greatest challenges in the search for life is the scale of the universe. Even the nearest stars are light years away. A signal sent today to a star 100 light years away would take a century to arrive. A reply would take another century to return. Interstellar travel with current technology would take tens of thousands of years. The universe may be filled with life, yet remain effectively silent and unreachable. Distance alone may isolate civilizations from one another. Time may be as important as distance. The universe is 13.8 billion years old. Earth formed relatively late. Life may have arisen elsewhere billions of years before us. Civilizations may rise and fall on timescales of thousands or millions of years, a blink of an eye in cosmic history. We may be searching during a quiet interval, or we may be among the first. Some scientists argue that Earth may be truly exceptional. Our planet has a large moon that stabilizes its climate. It has plate tectonics that recycle carbon. It has a strong magnetic field that shields it from radiation. It orbits a long-lived, stable star. Perhaps such a combination is extremely rare. If so, Earth could be one of very few worlds capable of sustaining complex life for billions of years. Others argue the opposite. The Copernican principle states that there is nothing special about our position in the universe. Earth is not at the center. The Sun is not special. The Milky Way is not unique. By this reasoning, life on Earth is not exceptional. It is a typical outcome of cosmic evolution. Which view is correct remains unknown. We can say that the universe is vast. We can say that planets are common. We can say that the chemistry of life is widespread. We can say that potentially habitable environments exist. We can say that life appeared early on Earth. We can say that we have not yet detected life beyond Earth. Everything beyond that remains uncertain. Why the question matters. The search for extraterrestrial life is not just about aliens. It is about understanding our place in the universe. If life is common, then Earth is one example among many. If life is rare, then our planet may be extraordinarily precious. Either answer reshapes how we see ourselves. The question of life beyond Earth is not a belief system. It is not speculation. It is an empirical problem. It will be answered by telescopes, probes, laboratory experiments, and careful observation. The universe is under no obligation to conform to our hopes or fears, but it is open to investigation. We stand at the beginning of a new era in exploration. For the first time in history, we can detect planets around other stars. We can analyze their atmospheres. We can search for chemical signatures of life. We can listen for distant signals. The tools now exist. The question is no longer philosophical. It is scientific. Are we alone? We do not yet know. But for the first time, we are finally in a position to find out.